Hello! Thanks for watching, and welcome to the next video in my series on basic statistics. Now, as usual, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, but you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can work through it. I have faith in you. Many other people around you have faith in you. So should you. Number two, please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way, when I upload a new video, you know about it. And it's always nice to connect with my viewers online. I feel that life is much too short and the world is much too large for us to miss the chance to connect when we can. Number three, if you like the video, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist. That does encourage me to keep making them for you. On the flip side, if you think there's something I can do better, please leave a constructive comment below the video, and I will take those ideas into account when I make new ones. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats. So I'm just going over basic concepts, and I will be doing so in a slow, deliberate manner. Not only do I want you to know what is going on, but also why and how to apply it. So, all that being said, let's go ahead and get started. This is the next video in our series about the analysis of variance, or ANOVA. More specifically, the two-way ANOVA. To make the topic more manageable, I have divided this video into two parts. In part 1, we will discuss the conceptual background using graphics and charts, and then in part 2, we will go into Microsoft Excel to conduct a hand calculation of a two-way ANOVA, and also solve our example using Excel's built-in data analysis tools. And just a word of caution, this topic is not easy. You may have to pause, rewind, or rewatch parts of the video to let the information sink in a bit. You must have patience and remain determined to learn. Okay, so in our last video, we took an in-depth look at the one-way ANOVA and what it offers us. Prior to ANOVA, we were limited to conducting hypothesis tests about a maximum of 2 populations. ANOVA frees us of that limitation, permitting comparisons of multiple populations and even subgroups, or what are called blocks of those populations. There are several types of ANOVAs. In this video, we will be focusing on the two-way ANOVA, which comes in 2 flavors, without replication and with replication. In this video, we will be learning about the two-way ANOVA without replication, also known as the completely randomized block design. Now, this video is very comprehensive. In part 1, I will use several illustrations to make concrete the abstract concepts underlying ANOVA. In part 2, as I said, we will go into Microsoft Excel and hand calculate the ANOVA, which, admittedly, you may never have to do, hopefully will not have to do. So this video offers a solid, comprehensive conceptual foundation of the two-way ANOVA using an example problem with illustrations and graphics. So, if you are new to ANOVA or are still trying to figure out exactly what it is, this video is for you. So, sit back, relax, and let's go ahead and get to work. So first, as a quick review, why ANOVA in the first place? So remember, prior to ANOVA, we had been comparing only 2 populations. We had the independent samples t-test, which are 2 random samples, or a matched sample t-test, or a paired t-test, where each measurement is sort of the same thing, measured maybe before or after, or something like that. Of course, limiting ourselves to the comparison of 2 populations is, well, limiting. What if we wish to compare the means of more than 2 populations? What if we wish to compare populations each containing several levels or subgroups? Enter the ANOVA, or the analysis of variance. So suppose we want to compare 3 population means to see if a difference exists somewhere among them. So we have population 1 there in the blue, population 2 there in the pink, and population 3 there in the green. So what we're asking is, do all three of these means come from a common, sort of larger population in the background? Is one mean so far away from the other two that it is likely not from the same population? Or are all three so far apart that they all likely come from unique populations? Now, there are several types of ANOVAs, and let's look here at Excel to see what it offers us. So in Excel, we have the ANOVA single factor, that's the one-way ANOVA, and then we have the ANOVA two-factor with replication, and the ANOVA two-factor without replication. So we're going to be looking at the ANOVA two-factor without replication in this video. This is also called the randomized block design, and we'll see how that applies later. So it goes by several names. It's the two-factor without replication. It can be called the two-way without replication, or you'll also see it as the randomized block design. So just keep that in mind as you proceed through your own coursework and through our videos here. So what is this two-way ANOVA block design? So remember, in a one-way ANOVA, we selected a random sample for each column or treatment group. Now, a two-way ANOVA allows us to account for variation at the row level due to some other factor or grouping. So in a one-way ANOVA, we had 3 or more columns. In the two-way ANOVA, we're going to add a second dimension, a row dimension, based on some other criteria. Now, by adding blocks or factors to the rows, we can subtract out that row variance from the overall error variance. And this is very important. We'll talk about why as we go. Now, this allows greater focus on the columns or the group differences, making it easier to detect differences in those groups. So adding the row variance in the block designs, sort of accounting for it, we can take that row variance out of the error, which means a smaller error variance. When we compare the smaller error variance to the column variance, it will give us greater sort of resolution to detect group differences in those columns. So we are attempting to minimize the error variance by saying, hey now, some of that error variance is actually due to the variance in the rows. So we're trying to assign some of the error variance to the rows because it kind of makes the columns look better. And I don't mean that literally. It makes differences in them or between them easier to detect. So we will now have 4 types of sum of squares. We're going to have the total sum of squares, the total variance, and that is made up of the group or column variance, the row and block variance, and the error variance. So this total variance of the problem is made up of these 3 other types: columns, blocks, and error. Now, just a quick side note here, progressing towards regression. Now, assigning or allocating a certain proportion of variance or variation to specific factors or variables is at the heart of simple and multiple regression. In fact, the explanatory power of linear regression is actually based on the ANOVA. So it's all tied together. And I make this quick note to sort of point out, to keep this one fresh in your head, and to sort of point out that as we go forward, we're building on the same concepts, we're just expanding them into new areas. So this partitioning of variance plays an important part in regression. So here is our example problem. We're going to call it Starbucks Down Under. So let's assume that Starbucks uses secret shoppers who appear to be customers to enter a store and document their experience in terms of customer service, the cleanliness of the store, and the quality of the product, coffee, latte, whatever else it might be. The secret shoppers receive standardized training by Starbucks to ensure consistency and objectivity in their store reviews. So for its locations in the Australian cities of Sydney, Brisbane, and Melbourne, Starbucks has trained 6 secret shoppers. Now, each of the 6 secret shoppers will be assigned to visit the same store in each of the 3 cities. Now, the visit sequence will be assigned randomly, hence the name randomized block design. So, just sort of a 10,000-foot view here. Starbucks uses secret shoppers to test the quality of the service, the product, and everything at their stores. Now, to the people working at the Starbucks, they appear like any other customer, but of course they're not. They're actually there trying to figure out how well the store is managed, how well it runs, and things like that, making sure it holds up to Starbucks standards. So, we would like to know if a difference exists in secret shopper ratings among the cities. Are all the cities about the same in their ratings? Is one significantly higher than the other 2? Or are all 3 different from each other? Now note, this is only testing for differences among the cities. It's not testing whether they are good or bad, which is a subjective experience, a subjective rating. They could all score 5 out of 100 on this secret shopper evaluation, and they would all be the same, but they would all be very bad. So we're only looking for differences. We're not saying whether or not they're good or bad, but the data will kind of point out which ones are and which ones aren't when we see it. Now, here's at the heart of what we're getting at. What makes this problem fit for a two-way ANOVA is that the secret shoppers themselves will have their own natural variation. And that's just sort of make common sense. We're dealing with human beings here that are looking at things in their own way. So the secret shoppers themselves will have their own natural variation. So the two-way ANOVA allows us to account for this shopper variation to better determine if a difference exists among the cities, without the shopper variation sort of clouding or masking any of the city differences. You can think of it as we are untangling all of the sources of variation. So we are really interested in the differences between the cities. But since we're dealing with 6 secret shoppers, we have to account for the natural variation that exists among the shoppers themselves and sort of untangle that, sort of extract that out before we can really get down to looking at any differences that might exist between the cities. So let's look at how we might set this up. So we can set up a simple table here. And along the top, we have our columns or our groups or our treatments. Depending on the problem, they can be called either one. So we have Sydney, Brisbane, and Melbourne. So this is our factor 1, our first factor, which is, of course, city. Now on the left-hand side, we have our blocks, and these are our secret shoppers. So we call this the blocking variable. Now each shopper will be assigned to all 3 cities and visit each city only once. However, the order in which the visits are made will be done randomly. So it may look something like this. So secret shopper number 1 will visit Brisbane first, and then go to Sydney, and then go to Melbourne. Shopper 2 will start at Sydney, and then we'll go to Melbourne, and then to Brisbane. So the point here is that the order that they go in is random, and that's why it's called the randomized block design. Now it's called without replication because each shopper is only going to each city once. So shopper 1's going to Sydney once, Brisbane once, and Melbourne once. Same thing for shopper 2, 3, 4, 5, and 6. So that's the without replication part. The randomized part is because the order they go in is random. So what is the purpose of this blocking variable? In this case, the secret shoppers. Now, ANOVA is all about teasing apart or partitioning the total or overall variance into different parts, sort of into different containers. So assigning parts of the overall variance to different sources. Now, one of these parts or one of these containers is always error variance. That's sort of the unexplained variance or the unexplained source. It will always be there. Now, in a one-way ANOVA, aside from the error, we were only working with one other potential source of variance, and that was the columns or the groups. So the vertical columns or groups, the three or more we were working with. So we had the variance of those columns, and then we had the error variance, and then we added those together, we got the overall variance. Now in a two-way ANOVA, we introduce a new way to separate the data apart, and that's by using blocks. Now blocks allow us to further refine how we assign or split apart the overall variance, allowing for a more powerful hypothesis test. So let's take a look at this graphically. Now the first thing we want to look at is the city variation, so the column variation. Now before we do that, let's look at this overall mean. So if we take all of these scores and we find the mean of all 18 scores, we come up with an overall or a grand mean, however you want to label it, of 70. So all 18 of those scores out of 100 here is 70. Now each city has its own mean and its own distribution. And again, I've color-coded them so you can see how they all match. So once we sort of get on the mean of those columns, we can see that Sydney had a mean of 67.5. So when we tally up all the scores for all 6 secret shoppers, Sydney had an average of 67.5. Brisbane had a mean of 65, and Melbourne had a mean of 77.5. So a quick look at these column means tells us what, in general, in very general terms? Well, we can see that Brisbane is the lowest. We can see that Melbourne is the highest. Now look at how each one of those is related or compares to our overall mean. So our overall mean was 70. So Brisbane was 5 below that. Sydney was 2.5 below that. And Melbourne was 7.5 above that. Okay, so we can kind of get a basic overview of how each city's mean compares to the overall mean of 70. Now a quick FYI before we continue. I just want to point out what a two-way ANOVA with replication would look like. And all that means when we say a two-way ANOVA with replication, we have multiple measurements per cell. So in this case, each shopper went to each city 3 times. And then that generates more data for each cell, and that's what we call a two-way ANOVA with replication. That's the only difference. So we'll do that eventually in this video series, but I just wanted to point out sort of visually what the difference is. Okay, so we looked at the column means. Now we want to look at our block means. So Sydney, Brisbane, Melbourne are our columns or groups. Now we're looking at our blocks, which is our rows. So each shopper will have his or her own mean and distribution. So shopper 1, when you tally up all that shopper's scores of 75, 75, and 90, that comes up to 80. Shopper 2 is 70, 70, 70. Well, that's 70. So you can see the mean of each row or each block. So down at the bottom we have city variation, down there in the red. On the right we have shopper variation as they compare to our overall mean of 70. So let's see how this works. Now, what we're doing, remember, I said in the first couple of slides, we're interested in partitioning or separating or splitting up the overall sum of squares. So remember in the one-way ANOVA, we had an overall sum of squares. And we'll show you how to do that here in a second. So the overall sum of squares is SST, for sum of squares total. Now we could attribute those sum of squares to two sources. That could be attributed to the columns. So SSC, sum of squares columns, and whatever wasn't SSC was error, okay, or sort of the within error sum of squares, the within sum of squares. So we have SST that's split into either SSC, sum of squares columns, or SSE, sum of squares error. Now when we added those two together, SSC plus SSE came up with, or was summed to, SST. We're literally splitting the SST into these two parts. That when you add them back together, gives us SST again. So this was the one-way ANOVA. So now we're dealing with the two-way ANOVA. So what we're trying to do is this original SSE that we had, remember, in the one-way, sort of there on the bottom right. What we're going to try to do is separate this out even more. I call it sort of eating it up, sort of gobbling it up. So we introduce this blocking variable, and in this case, it's the 6 different shoppers. So we're going to split this original SSE, the sum of squares error, into either the blocks or remaining error. So here in this first case, we can say, well, 50% of that original SSE actually belongs to the blocks, and the other 50% is still error. Or it could be like this. 25% of that original SSE belongs to the blocks, and the other 75% is still error. Or it could be this way. The 75% of it is part of the blocks, and the other 25% is still error. So what we're trying to do is separate out the variation due to the blocking variable from the remainder of the SSE, or the error. Now here's the most important block probably in this part 1. So here's what's going on. Remember, we're interested in the differences between the cities, or the columns. So the sum of squares columns, or the SSC, wants the SSE, the sum of squares error, to be as small as possible. So it's kind of saying, hey, sum of squares blocks, eat up as much of that original SSE as possible. Chomp, chomp. So the SSC wants the blocks to gobble up as much of that original error as possible. And why is that? Well, in the end, the sum of squares columns will be compared to the SSE. So the smaller the SSE is, the sum of squares columns can claim a larger part of the total variance. Okay? So again, I'm going to show you some graphics here in a minute to actually, to make it more concrete. But the idea here is, by introducing this blocking variable, we're going to partition or separate the original SSE into SSB and remaining SSE. Now, the columns want the blocking variable to gobble up, or to eat up, as much of the SSE as possible. Because when the SSC is compared to the SSE, it wants the SSE to be as small as possible. That's what we're trying to do here. So hang with me. We'll see how this works as we go. Okay, so partitioning or separating this total sum of squares. So we have SST, that's our overall sum of squares. So over here we have the SSC, so the column or group sum of squares. Now we started off in a one-way ANOVA with this sum of squares error. So kind of have this gray blob over here, this gray block that is our original SSE. So basically it's anything that's not, or any variance that's not SSC. Now in the two-way ANOVA, we're going to take this and split it up. Some of it will be SSB, so it will belong to the blocks, and what's left will be error, so SSE. So as we progress from one-way to two-way, all we're doing is splitting up the original SSE into blocks and then remaining SSE. Now again, SSC over here on the left in the red wants this SSE down here on the lower right to be as small as possible. Because when we set up our F ratio later on, if the SSC is much larger than the SSE, then we can detect those differences in the columns. And again, we'll see how this works as we go. Okay, let's look at SST first. What are we actually doing here? So we're finding the difference between each data point and the overall mean. So each of the 18 data points and this overall mean of 70. So once we find that difference, we square it. And then we add them up. That's why this is called sum of squares. So we take each point, we find the difference between each one of those 18 points. I only circled 6 here because of room, but we find the difference, square that difference, and then add the differences up. Sum of squares. So visually it might look something like this. So this distribution in the background is our overall mean of 70, and then here we have each of our 18 data points. So we find the distance to that mean, and then we literally square each distance. So it's when we say sum of squares, we actually mean that literally. It is literally the sum of squares, because we're squaring that difference. Okay, so how about column means? Sum of squares column, so SSC. This is really what we're interested in this problem. So each city, Sydney, Brisbane, and Melbourne, based on the shopper data, has its own mean, you can see down there at the bottom, and its own distribution. It has 6 points, 6 data points. So what do we do here? We find the difference between each group mean, there along the bottom, and the overall mean of 70. Square those deviations or those differences, and then add them up. So in this case, we have 3 squared deviations. So each one of the city means, or the group or column means, find the difference with the overall mean, square those differences, add them up. So here we have our distribution in the background of 70, or the mean of 70, the overall mean. And you can see each city placed relative to that mean. So we have our second city there in the pink is pretty far away at 65. Our first city, which I believe was Sydney, was there at 67.5. They're in the middle in the blue. And then Melbourne, I believe it was, is over on the right here in the green. So the distance from each column mean to the overall mean of 70, and again, we square them and add them together. So now what about blocks? So again, this is everything we've done so far has been part of the one-way ANOVA. Nothing's been any different than it was in the one-way ANOVA. But now we have the blocks. So this is where the two-way ANOVA sort of forms its identity. But it works the exact same way. So we find the difference between each row or block mean over there on the right, and the overall mean, which is still 70, of course, square each difference or each deviation, add them up, and then that will be our sum of squares for the blocks or for the rows. So we take each row mean, find the difference with the overall mean down below, square the differences, and then add them up. Same process. It's squared differences, squared deviations. So it might look something like this. So we have each row or each block have its mean, and then how it relates to that overall mean of 70. Same idea. Okay, so just remember that we have three types of sum of squares. We have SSC, which is our sum of squares of columns, again, which is the mean of each column as it relates to the overall mean. Now we have SSB, which is the mean of each block as it relates to the overall mean. And then we have this thing called error. Now when we add all those together, they come up, or they sum up to our SST, or sum of squares total. So SSC plus SSB plus SSE adds up to SST. Now, of course, using algebra, if we can calculate 3 of the 4 of those, then we can find the last one just by subtraction. So again, just basic algebra. We can find 3 of the 4, we can solve for the 4th. So finding the error sum of squares, or the SSE. So this is what we had before. So SST equals SSC plus SSB plus SSE. Now we can rearrange that algebraically. So now we have SSE, which is our error, equals SST minus SSC minus SSB. And again, that is just simple algebra to solve for the SSE. So how much overall SSE did our sum of squares blocks, or SSB, account for? Because remember, we're trying to assign that overall SSE from sort of the one-way ANOVA, introduce blocks, and then have those blocks extract some of that variance out. So we want to know how that did, or how it works. So we're interested in the relationship between block variance and error variance. So if you remember those 3 graphics I had on the right, where I said the blocks accounted for 25% of that original SSE, or it accounted for 50% or 75%, that's what I'm talking about here. How much did it eat up? How much did it gobble up of that original SSE? Now we can figure out this relationship by setting up a simple fraction. So sum of squares blocks divided by sum of squares error. Okay, so it's a ratio. So SSB divided by SSE. Now we don't actually divide those two things. We introduce this concept of degrees of freedom. Now I'm saving that for the second part of this video, so don't worry about degrees of freedom, but no, it comes into play when we actually do this comparison. Now when we divide by degrees of freedom, we end up with mean square blocks. So dividing by degrees of freedom gives us the mean of those sum of squares. But the idea here is the same. So we have block divided by error. And that's going to tell us our relationship. And again, I'm going to go into this in part 2 more in depth, but I just want to show you how we figure out how much of the block variance was gobbled up from the original MSE. Now, since this is a ratio of 2 variances, if you remember from previous videos, we will be using the F ratio, and it will follow the F distribution. And that is why when you look at an ANOVA output in Excel or SPSS or SAS, whatever it might be, it will give you an F ratio, or it will give you an F test, or an F value with a significance. Well, here it is. This is where it comes from. So again, why try to minimize the SSE by introducing blocks? So remember that we are really interested in SSC, or our column or group variance, which in this case is cities, as part of the overall sum of squares, which is SST. SST is total. But we need to account for the variation between the secret shoppers. So anything that's not in the columns, or cities, is error. So if we were doing this in a one-way ANOVA, we would have sum of squares total, and then that will be split apart into SSC, or columns, or cities, and SSE, which is everything that's not SSC. Now, by introducing blocks, this allows us to potentially reduce that original SSE even more by splitting the original SSE, as in a one-way, into SSB and a smaller SSE. And again, that's my point about we want to introduce the blocks to try to eat up or gobble up that original SSE, and that is done by accounting for the variation of the shoppers in this case. Now, if the SSC is much larger than the minimized SSE, then there are likely group or column differences. So you can see here that the whole idea of this blocking is to minimize the sum of squares error. So we introduce the blocks that allows us to minimize the error component of the variance and assign some of it to the blocks. So when we compare SSC to SSE, it's usually smaller. So comparing SSC to the minimized SSE makes the test more powerful and more sensitive. So the SSC relative to the SSE is greater because we've accounted for a large part of that original SSE in the blocks. And that's the whole idea behind a two-way ANOVA completely randomized block design, in this case without repetition.